Okay, so today we are going to talk about a new term called impulse. The CK12 that you guys watched had impulse in it, so there was some background knowledge that you should have on what impulse is. We're going to relate it today to momentum. Technically, impulse and momentum are very similar. They're going to have a different math equation, but why we call this the impulse momentum theory is that we're going to show you how impulse basically equals the change in momentum of an object. So they will equal each other out mathematically, but we start from two very different equations just to solve for them on their own. So we'll do a little bit of both. But just as a reminder from the CK12, since it was a couple weeks ago, let's do a brief little conversation about what impulse is. So impulse is a very, very important concept, especially when we're talking about sports safety. So sports safety equipment, car crash safety. Impulse is probably one of the biggest physics terms that they use in order to reduce the amount of force on your body, which is obviously the goal, because if you're in an impact, in a crash, you want the least amount of force on your body so you can survive. So that is the idea behind impulse. Think about all kinds of different situations. One simple one, you jump from something high. Maybe you're climbing over a fence and you're jumping down. When you jump down, you don't land with your legs straight. You land and you bend your knees towards the ground as you kind of fall down towards the ground, or bend your knees to, a lot of people would say, absorb the force or absorb the energy from that jump. That's very true, but really you have a built-in impulse system right there. By bending your knees, you're allowing for more time for your body to come to a stop. If you landed straight-legged, you would come to a stop right away. And inside, your body would feel all that force. Your bones could break, your knees could hyperextend or um, overextend, or anything that could happen inside your body. Your back could get injured, would be because you came to a stop too quickly. So instead, naturally, we bend our knees. And you might have seen parkour, and a lot of times in those parkour videos, those people are jumping from really high places down to other places, and every single time they not only bend their knees, but they'll roll through their landing, and that helps them increase the amount of time that they're coming to a stop. Um, just to draw really quickly, we also have them in cars all the time. One of the biggest things that saves people's lives now is that airbag that comes out. So if a person's face is going to hit an airbag, the moment that the airbag is released, there has to be a very quick amount of time that it's not just on its way out when you impact. You want it to actually be starting to deflate once you make impact. Because imagine if you were hitting an airbag going outward, you're going to be like impacting a wall. So they want to make this airbag deploy extremely quickly, so it's so quick that it's starting to deflate by the time your face impacts it. Okay? So what that means is, by the time your face makes contact to when it comes to a complete stop as the airbag deflates, that's going to increase the amount of time that your face will come to a stop. That time interval there, the more time there is, the less force your face will take. Okay? Now imagine if you didn't have an airbag and you were just going to impact the steering wheel. Okay? So you have your steering column here. I'm terrible at drawing, you guys know that. And your face is going to now impact that. It's hard. It's not going to increase the amount of time. The amount of time your face is going to come to a stop is literally not even enough to draw. This one I could draw because the deflation of the airbag. Your face would hit a hard surface and come to a stop almost instantaneously. That means you're going to have a huge amount of force. Where here in the airbag, we had a really low amount of force. Okay, so that's the idea of impulse. Like I said, your knees are built-in impulse machines right there. They're meant to take that time to come to a stop in order for your body to experience the least amount of force. Okay, so that's the idea of impulse. There's so many different examples in sports. All of the safety equipment, when you wear knee pads, when you wear helmets, when you wear pads for football, when you wear shin guards for soccer, when you wear boxing gloves if you're boxing. All of those are increasing the amount of time that your hand or your knees or your body or your head is going to come to a stop, and increasing that amount of time. So basically adding cushion, right? Increases the amount of time, reduces the force on your body. Safety, that's the important part of it. Okay, so that's the conceptual part of impulse. Mathematically, we're going to look at how it also is the same as momentum, but thinking too, changing your momentum means when something's moving at one momentum and suddenly it goes, maybe it slows down, hint, hint, the velocity decreases because maybe it's impacted something that's helping it slow down, like an airbag or a mat if you're a high jumper. Okay, you've now gone from a high velocity to a lower velocity. You've also changed your momentum. Hey, change in momentum equals impulse. So we're going to see how that works out. Okay, so first let's get a definition of impulse. And I'm sorry because I'm working in my room and I have can lights above me. I have this terrible shadow. So I'll always try to make sure that after I write it, I give you a good glimpse of what it is and keep my shadow out of the way. So what does impulse? Impulse is the product, so it's another multiplication variable, or multiplying variables to get impulse. It's the product of the average, probably should spell average, right, huh? Forgot the A. Of the average force and the time interval which the force acts. Oh, during which the force acts, sorry. The time interval during which the force acts. Okay, so you can see that the average force is going to be important. And then when we start looking for force, instead, we'll rearrange the equation using impulse and time. But force and time are going to be what gives us impulse. Okay, so let's look at the equation then. So for impulse, we actually use a new variable, which is what we call J. So J is the impulse variable. So it's not I, it's J. Okay, so impulse equals the product of force. You see that? So it's the average force. And we're multiplying that by the time interval, or the change in time. So T stands for time. So when I say change in time, you may see in the equation just having a T without the delta. Just remember, it's not a single point in time, it's the change in time. So if you are hitting your face on an airbag, by the time you impact it starting is 0, and then whatever time it takes to come to a stop, that's your ending time. So that's the change in time that matters. The longer the change in time, the better. The shorter the change in time, the more harm you're going to have done. Okay, so sometimes that delta might not be in the equation, but always remember it is a change in time. It's a time interval and not just a point in time. Okay, this does have a circle. So any of our multiplying equations have the circle, J on top, force and time on bottom. Okay, so we can rearrange it using any of those methods of covering. So if we're looking for time, we get impulse divided by force. If we're looking for force, we get impulse divided by time. And then our basic equation, if we're looking for impulse, we have force multiplied by time. All right, so there is units. And let's talk about what we already know. We've used force and time already in equations, so we know their units. So we know that we use time in seconds. So that's going to be our unit for time. We've used force before. Remember, force was mass times acceleration, which is a kilograms times a meters per second squared, and we gave that a new name called the Newton. So force is in newtons. And so when we multiply a Newton times a second, we're going to get exactly that, a Newton second. So impulse is measured in a Newton second. So that might sound a little bit weird. We've got all these different units, but just think about it. Whatever you're multiplying together is going to equal what the unit is. Occasionally, we do change the name of the unit, like for a Newton. We don't use kilograms meters per second squared. We change it to a Newton, but it's pretty common now. You've heard it a lot. You heard it in force and weight. So just remember, that's a Newton for force. Okay, Newton times a second equals a Newton second. Now I'm going to put the momentum equation here as well. So this first one is impulse, but I'm also going to put momentum out here so we can compare them, because the whole idea is we want to see how impulse and momentum are the same. So it's called the impulse momentum theory. And we will do practice problems for both. So P is momentum. Remember that? I know you already have these notes, but just write them down here again for the fact that we're going to compare them. Equals mass multiplied by velocity. We just have been doing that. So again, for the units, we know velocity is meters per second, mass is kilograms. You get a kilograms meters per second because we multiply them together. And just for sake of the circle, we also have a momentum circle. P equals m times v. Okay, so now looking at those, you might say, how are these the same thing? These don't make sense. We have none of the same units, time, velocity, force, mass. How are these impulse and momentum going to be the same? Okay, so let's figure that out. And we'll write the question. How does impulse equal change in momentum? And we're going to use, in here, we can actually find that there are parts of other equations we have done. Okay, we've used force before, we used velocity, we've used time, mass. Okay, these can be broken down using Newton's second law. Now, stay with me because right now you're like, what the heck? That's confusing. I don't even know what you're talking about. Newton's second law, impulse, momentum. So all these relate to each other. We've talked about how momentum relates to the amount of force applied originally. Remember, a momentum is an object in motion. So to get something in motion, you had to have a force applied to it. Okay. Impulse is going to equal change in momentum, and we're going to use Newton's second law. So we have to remember the equation for that. So let's go ahead and we're going to break this into two sides. We're going to do the equation side, and we're going to look at the units, because remember I told you units always work out. So I'm going to move down a little bit so y'all can see. So units always work out along with the equation. Remember, if we're canceling units on top and bottom, they always equal the units we need. So it's not by coincidence, it's because it works out that way in the equation. So I said we're going to use Newton's second law. So let's start with Newton's second law. So step one, let's write out Newton's second law. Remember, the equation for Newton's second law of motion is force equals mass times acceleration. Okay, so let's start there. And let's see, using mass times acceleration, let's go ahead and see what we know about that in here. Okay, we have that force in here. We got mass times acceleration. We also know that acceleration itself can be broken down. Acceleration technically means the change in velocity. Remember, we got velocity here, and we got time. It's the change in velocity over a certain amount of time. So right there, we have some variables in here that we can start to break down. Can't really break down mass. Mass is mass. Okay, we can break down force because force is mass times acceleration. So we already know force is mass and acceleration. But we can go further with acceleration. So let's break acceleration down. So acceleration is going to equal the change in velocity over time, remember? Because we did that in the beginning of the year. We did acceleration, which is final velocity minus initial velocity. That's the change in velocity over the amount of time. So if I'm getting on the freeway and I accelerate from 25 to 60 over a certain amount of time, that's my acceleration. Now, all I'm going to do is bring the mass straight down and the multiplication sign. Everything else is going straight down. And I'm going to say equals force. So all I did was took acceleration and broke it down into its actual variables. So now we're starting to get a little closer here. Let's go back up here. We've got a mass, we've got a force, we've got a time or change in time, we've got a velocity. Change in velocity is the same thing, right? The idea is it's still a velocity when we report it. So you're starting to see these variables come out. That's step 2 that we've seen before. Now, the last thing I need to do is I'm going to show you right here, we have all the makings of momentum and impulse. They're just in the wrong order. Okay, so we have the makings of momentum, mass and velocity. We have the makings of impulse, force and time. Mass and velocity, force and time. They're just not rearranged the correct way. So we need to have force and time together on this side of the equation, and we need to have mass and velocity together on this side of the equation, and that's how they will equal each other. So let's go ahead and see how we would do that using algebra. If I need t to be removed from this side and moved over to this side, it's currently being divided, okay? So I'm going to multiply it by the reciprocal, which would be t over 1. If I do that, I can cancel out the t that's on top and the t that's on bottom. Now I've just got rid of it, but remember what I do to one side of an equation, I have to do the other. So I also have to multiply this side by t over 1, which is technically, I don't need the 1, but we're going to do it for sake of being thorough. And let's go down here and make this look a little prettier. So now I have t times f. So I'm going to turn it into, I'm just going to flip it around, force multiplied by time. So let me give you a hint. Here we go. Force multiplied by time. There's impulse. And remember, I said, don't worry too much about the deltas. Change in velocity, change in time, those are important. But note that they can be reported in a problem as a single number instead of 2 numbers that you have to subtract. Equals, so I did this side, force multiplied by time. So here it is. I just flipped them around to make it look more like the impulse equation. Equals mass times change in velocity. Or mass times velocity, which we said is momentum. But remember, I said up here, we're going to prove that impulse equals change in momentum. So if I'm changing the velocity of an object, I'm changing its momentum. Okay, so right there is our fancy little equation. Okay, force multiplied by time equals mass multiplied by the change in velocity. So impulse equals change in momentum. Now, am I going to ask you to do this whole process on your own? No. I'm just showing you how do they equal each other. How does impulse equal change in momentum? Mathematically, we just showed you how, all through just rearranging the equation. Now, I'm going to turn it into its actual variables. So we're going to go one step further. We know that force and time equals impulse. We know that mass times change in velocity is going to give us change in momentum, or delta P. And just for the sake of all the triangles, remember, delta is the triangle, which equals change in. So change in time, change in momentum, change in velocity. Okay. So again, just think about that as the momentum is changing. You had one momentum initially, object was in motion, its velocity suddenly changed, and now it has a new momentum. All right, let's look at the units. How in the world does the units work out? Because up here we are with a whole bunch of different units again. We've got a kilogram, we've got a meters per second, we've got a second, we've got a Newton, we've got a Newton second, we've got a kilograms meters per second. How do those all work out? Well, if the equation works out, shouldn't the units work out? Yes. Okay. So let's actually start from the bottom. We're going to go with the fact that we're going to start from J equals change in momentum. Just because we know the units for J, which is impulse, and we know the units for momentum. So let's go ahead and look up here just for the fact of seeing what we wrote. J is a Newton second. Okay, so it's a Newton second equals, what's change in momentum? Well, it's just momentum, the unit, kilograms meters per second. So if these equal each other somehow, we've got to figure out how in the world do they equal each other. How does a Newton second equal a kilograms meters per second? Now remember, a kilogram and a meters per second are pretty much broken down all the way to their basics. But newtons aren't. Newtons actually mean something else, right? A newton is a mass times a an acceleration, a mass times an acceleration, which is a kilograms times a meters per second squared, okay? So we're going to break down the newton first, because just like we did in the equation, we broke down acceleration. We're going to break down the newton because it can be broken down. So step 2, a newton is going to be a kilograms meters per second squared, but I'm not done because I have to bring down the second as well, because we're not done, times a second. So we have a a kilogram meters per second squared times a second equals, we're still over here, kilograms meters per second. So you can see that this side hasn't changed at all. We just broke down the newton. Now we're getting closer though. We have kilograms and meters per second. We got some extra seconds over here that we got to get rid of, right? So I'm going to write it out in step 3, the way it would look in a math problem, where we have a meter per second, because that's what a meters per second squared is. So I'm just changing the meters per second squared to a meters per second. And I'm multiplying by a second. Okay. The issue here is this is a second over 1, technically, so we've just kind of made a fraction about it. So that means I can do some canceling, and I'm going to keep the other side the same, kilograms meters per second, because nothing can change on this side. Nothing can be broke down. But over here, now I have a second on top and a second on bottom. Boom, I just did it. It was that simple. Number 4 is going to say, now that I've canceled out my extra seconds, a kilograms meters per second equals a kilograms meters per second. That's how they equal each other. Oops, sorry, couldn't see me there writing that. That is how they equal each other. We have impulse equals change in momentum. Impulse equals change in momentum. So if you Googled the impulse momentum theory or theorem, they're going to tell you all of this information in words. All we did here is prove it. We took the equations and said how they equal each other. And then we took the units and showed how they equal each other. All right, let's do some practice. And we will talk more about that as time goes on. But for practice, first we're going to start with some impulse problems, okay? And then we're going to do some change in momentum problems because we have both. We've done momentum, like finding a single momentum of an object at a given time, but we haven't done change in momentum. What happens when the momentum changes within a problem? So an object slows down, okay? So we're going to do both of those. Let's start with impulse though. So examples, let's do a golf club. Oh, goodness, my pencil always breaks. A golf club strikes a golf ball with 16 newtons of force for 0.006 seconds. Now, you got to think about that. The impact time of a golf ball and a golf club are going to be really, really small when you're striking a golf ball with the club. So these numbers for time, sometimes are going to be really, really small. Don't let that freak you out. Just plug them in the same way. What is the impulse? All right, so we have a golf ball with 16 newtons of force. We have a time of 0.00 seconds. We're looking for impulse. Okay, so we need to solve. We're going to need a J, and we're going to need an F, and we're going to need a T. Now, you're going, wait, how is that a change in time? Isn't that supposed to be change in time? Well, yeah, the minute it touched the golf ball was 0. The minute it left, or the golf ball was released from the club, was 0.00 seconds later. So it was such a small contact time. So think of the scenario too. It's a small contact time. So that's why the number is so small, but it is still a change in time. It's an interval of time. So J is what we're looking for. Remember, that's going to be X, and remember, it's a Newton second because impulse is force multiplied by time. The force on the object is 16 newtons, and the time of contact is 0.006 seconds. So we are looking for impulse. So our base equation is J equals F times T, or delta T. I am going to plug in what I have, just like we've done for every other equation. X Newton seconds equals 16 newtons multiplied by 0.006 seconds equals. So now I just need to plug that into my calculator. So I'm going to go 16 times 0.006 equals, and I get 0.096 Newton seconds. There we go. And that is the impulse. Now, some of you might say, well, I don't understand what this number means. It doesn't make a lot of sense. You're right. We're really trying to make this number, when we're talking safety, as low as possible on objects so we don't break them. Certain things can only withstand a certain amount of force, your body being one of them. So, yeah, well, scientists would look at this number and say, oh, okay, we need to understand the impulse, but really, things we can control is the amount of time. That's how they manipulate the impulse to also manipulate the force. So that's what's really important. Okay, 2. A high jumper. So it's a track event. Hopefully you've seen high jump before. High jumper lands on a mat, and they have really thick mats because if you've watched a high jumper, they jump over the bar backwards and land usually on their shoulders and back and head with a time of 0.64 seconds before stopping. Now you might say, well, that's not very long, but that's still a long time in comparison to how long the golf ball was in contact with the golf club. That's a half a second that they're actually impacting and coming to a stop. So they're not jumping from super high, but like a pole vaulter, they're going to go even higher. They come down from 13, 14. Really, really good pole vaulters are 16 feet. They're up there coming down and landing on a mat. So their time would be longer because they are falling farther. So they're taking that time before stopping. Their impulse is 550 Newton seconds. What is the force on their body? And you know what? I think, did I do that right? I think I might have put 1.64 in my notes. So hold on really quickly. Let me look at that and then I'll be right back because I don't have my notes on me. I'm going to pause it. Okay, never mind. I'm not going to pause it. It's not letting me pause it, but let me just do it really quickly before I write it down for you guys. Yeah, I did. This is 1.64 seconds. There we go. I was going to say that number looked funny when I wrote it down. I'm like, that's pretty short. 1.64 seconds. What is the force on their body? All right, back to where we're at. So we need the equation. So I'm just going to throw the circle over here so we can look at it. J on top, force and time on bottom. We are now looking for force. We have the time and we have the impulse. So we want to know force, so we're going to cover up F. That gives us impulse divided by time, J on top of T. So our equation will be force equals J on top of T. So we need a J, F, and T, because those are our variables. And we have 550 newtons seconds for our J. There we are. We need force, which is going to be X newtons. And we're given time of 1.64 seconds. There we go. So the high jumper sinks in to the mat before coming to a stop. You wouldn't want to land on the ground as a high jumper. So we're going to plug in these numbers into the equation. X newtons equals, our J goes on top, so 550 newton seconds. And we're going to divide that by our time of 1.64 seconds. So just like before, we plug it into our calculator and we get an answer. So we have 550 divided by 1.64 equals, that's going to tell us 335. And we can go ahead and go, significant digits tell us we can just leave it there. We don't need all the decimals. So we'll just leave it there and say cancel seconds on top, seconds on bottom. That leaves us newtons. That's what we're looking for. 335 newtons of force on the body. Okay. Number 3. So we looked for impulse, we looked for force. Let's look for some time. Move it up for you guys. How much time? Is needed to stop an object with 1,250 newtons of force and an impulse of 1,860 newton seconds. Okay, so now this time we're looking for time. How much time is needed to stop an object? So this object's in motion, remember? Because impulse and change in momentum are technically the same thing. So it has to be moving. With 1,250 newtons of force and 1,860 newton seconds of impulse. So J, F, and T, let's write down our variables and then we'll get our equation. J is 1,860 newton seconds. Force is 1,250 newtons. Time is X seconds. So we're going to be looking for time. Let's go back up to our little circle up here. Cover up T. You get J divided by F. So our equation is T equals impulse divided by force. All right, let's plug it in. X seconds equals J on top, 1,860 newton seconds, divided by 1,250 newtons. That's our force. Newtons cancel this time. We're left with seconds. That's what we need, so we're on the right track. So then I just divide. Oh, there's my kids. 1,860 divided by 1,250 equals 1 point. And let's go 488. So I went out 4 digits because both of those numbers are 4 digits. If you round it up and you go 1.5 or 1.49, that's fine too. I'm not really picky on that because we're not supposed to be really teaching you the significant digits, but I'm just going to go out to this. Seconds. So So if you said 1.5 or 1.49, that's fine too. All right, that is the amount of time, though, it needs to stop this object that has this much force and this much impulse. All right, so that is impulse examples. So at the top, if you didn't do that already, let's write examples and then let's put impulse, because we're going to do change in momentum examples next, and we want to make sure we know the difference. Okay, so impulse was that first section, just using the J equals F times T. So now we're going to talk about change in momentum examples. Holy moly, I can get my camera to cooperate. There we go. So examples, change in momentum, which technically is impulse, right? Because we just proved it through that theory. All right. But we're going to have some different information in this. We might have some velocities and whatnot. And there, since it's a change in momentum, we're probably going to have a change in velocity. So with this one, let's just really quickly go back to our notes before we move on. So our notes are telling us that impulse and momentum equal the same thing. And up here, we put the regular equations, the impulse and momentum. But down here, we found out that impulse and change in momentum equals the same thing. J equals change in momentum. So we could say this is the equation, but we're actually going to be looking at this section here because this is all the variables we need. This is just the final outcome, impulse equals change in momentum. This is the variables we need to make this work. We need F times T equals M times change in velocity, or change in V, okay, delta V. So let's write that down at the top so we have that in our mind while we're doing this. So the equation we're going to be using or looking at the whole time is force multiplied by time, that's the impulse part, equals mass times change in velocity, or delta V, which is the change in momentum part. So that's the equation we're going to be focused on. So the math on this is going to be a tiny bit different than what we've been doing, because now we have two variables on each side instead of just one that we're solving for. So we're going to have to do a tiny bit of algebra, but it's pretty easy. All right, so one, a car with a mass of 500 kilograms starts from rest. Holy cow, I keep breaking this. I'm going to run out of lead before I'm done. Starts from rest. Okay, so we know it's got a 0 velocity as a start. The car is pushed with 2,000 newtons of force for 3 seconds. What is the velocity after 3 seconds? Okay, so you're like, wait, I thought this was change in momentum. It is, because change in velocity equals a change in momentum. So we call these change in momentum problems, even if we're looking for F or T or M or V. Okay, so right now we're going to be looking for the ending velocity. We have the starting velocity, starts at rest. Remember that from acceleration, that change in velocity starts from rest, so it's 0. We want to know what it ends at after we've pushed it for 3 seconds. Okay, so we have to have all 4 variables in our equation. So we need an F, a T, an M, and a change in V in this case. We're going to be looking for that. So our force is given to us. Our mass is given to us. Our time is given to us. We want the ending velocity, or the velocity. So ultimately, we're going to be looking down here for the V. And that's also going to be the change in V, because it went from 0 to whatever velocity it ends up. So let's write down our variables. 500 kilograms is a mass. I need a new pencil, guys. 2,000 newtons is our force. 3 seconds is our time. We're looking for the velocity or change in velocity, which is going to be meters per second, x meters per second. Oh, there we go. X meters per second. So here's the thing. We're going to stick to using this equation every time. And now for sake of writing it, because, sometimes it's not fun to write all of the stuff out, I'm just going to write that just so I can remember I have an F, T, M, and V. Those are my variables. Yeah, it's changing, but it's okay. I need these 4 variables in my equation. Now the key is I need to find velocity. That means I need velocity by itself because I want to solve for V. So over here, I need to get V by itself. So just like we did in that last little theory that I was showing you with the equation, if I want something by itself, I have to move the other variable away. I want V by itself. I need to get rid of M. So I'm going to do that right off the bat. So there's not a fancy circle right now, but I'm just going to move M. If it's on the top of the equation, I can move M by dividing it out. Gone. Now V is alone. But whatever I do to one side, always got to do to the other. Super simple. Move my M over there by dividing it out on the other side. Now I can write it out correctly and say I have V by itself, so V equals, I'm just writing it backwards because M's gone, force multiplied by time, that's on the top over here, divided by mass. There's my equation. Now if you wanted to plug in all the numbers and divide out the numbers before you worried about, instead of worrying about, making the equation first, that's really fine too. You can plug in the force, plug in the time, plug in the mass, plug in x for velocity, divide out the mass, all of that works too. I just wanted to show you how the equation would look and how we got to this equation without putting numbers in it yet. So now I'm going to plug the numbers into this equation. My velocity is x meters per second. That's what I'm looking for. My force is 2,000 newtons. Multiplying that by my time of 3 seconds. So I have 2 things on the top now that I have to deal with. That's okay. It's not hard. Divided by my 500 kilograms of mass. So remember in math, you have to solve everything on top of a fraction before you do the division part. So I need to solve this on top, which is 2,000 times 3. So most of us probably can do that in our head. 2 times 3 is 6, so it's going to be 6,000. Now look I have a Newton times a second. Ooh, starting to see stuff I've noticed before. Ooh, impulse, right? But I'm going to divide out a kilogram here. So we'll see how that works. Divided by 500 kilograms. Now, you might go, wait, there's no kilograms on top. There's nothing on top and bottom I can cancel. Remember, a Newton is broken down into a kilogram meters per second squared. Okay, so if that's broken down into a kilograms meters per second squared, my kilograms are technically canceling out. Now I have a meters per second squared times a second, okay, on top because there's nothing on bottom anymore. So if I have a meters per second squared, we just did that a second ago, a meters per second times a second over 1, cancel out the seconds on bottom. I'm left with just a meters per second. Oh, that's what I need. And you know what? Because of the fact that I have no room, I'm going to do it below it. But you could probably do this, some of you, in your head. But I'm going to just type it in the calculator just so we can all see it together. Divided by 500 is going to be 12. Okay? Because 60 divided by 5 is 12, right? So 12 meters per second is our answer. I know that's a lot of gibberish up there, and you may not even care about that because you know you're looking for velocity, so therefore you know your unit has to be in meters per second, but units always work out. That's why it's really cool to see that, because they work out the exact same way the equation does. Okay, let's do number 2. How long must a tow truck pull with a force of 485, I'll move up because I know I'm getting out of space there, newtons on a 1,300 kilogram car, so that's its mass, to give it a velocity of 2.5 meters per second. Okay, so that's a lot of numbers in there. So we have 485 newtons, that's our force. We have 1,300 kilograms, that's our mass. We have 2.5 meters per second, that's our time. Now it's saying how long must it tow? So remember, this is our velocity down here. I don't know why I said time. How long is the time? Because it's how long must it do something. That's implying time. Sometimes words are funny, right? Long sometimes means distance, but in this case, how long means time. So we have all four things we need. So let's rearrange our equation like we did before so we can figure out how we're going to get time now. Force and time equals mass times velocity. Again, it is technically change in velocity, but we're assuming it started at 0 because I only gave you one velocity. I didn't give you more than one for you to figure out. So its change is going to be 2.5 meters per second, 0 to this. So if I want to find time, I need t by itself. That means I got to get rid of the f. I got to get rid of it so it's on the other side. So if I'm getting rid of f, I divide out f. That leaves t alone. So the rule of thumb I always remember is divide out the opposite thing I'm looking for. So if I'm looking for t, divide out f. If I'm looking for f, divide out t. If I do it to one side, I have to do it to the other side. That leaves me with t equals m times v divided by f. So if I wanted to write it one more time, just clearer, m times v divided by f. So time equals mass times velocity divided by force. So let's write down our variables. We have our force, our time, our mass, and our velocity. Our force is given to us at 485 newtons. Our time is what we're looking for. So it's x seconds. We have a 1,300 kilogram car, and it ends up at a velocity of 2.5 meters per second. That was its change in velocity. So I can put that delta there just so you remember that was its change. It started at 0, went to 2.5. So since I'm looking for time, t, x seconds equals my mass, which is 1,300 kilograms, times my velocity, 2.5 meters per second, divided by my force, which equals 485 newtons. So remember, you have to multiply everything on top before you divide. So I want to do 1,300 kilograms times 2.5, and that's going to give us 3,250 on the top and a kilograms meters per second. That's the momentum, right? Divided by my force, which is 485 newtons. Remember, in newtons is a kilograms meters per second squared. So technically on top, I have a kilograms meters per second, and on bottom, I have a kilograms meters per second squared. If I wrote this out the right way, I have kilograms meters per second. I can get rid of the kilograms and get rid of the meters per second. I'm left with one additional second. And guess what? We're looking for time. We need that second. So I'm going to do the division. 3,250 divided by 485. Almost am out of lead. Ooh, let's make it through these notes. Is going to equal, oops, sorry, I moved the thing. It's going to equal let's just go 6.70 in this case. And that is seconds. We won't go out further than that. It's not, like I said, you guys are supposed to learn significant digits in chemistry. You may have done them in math, so that's awesome. But next year, for sure, in chemistry, you'll do it. All right, so that's just two examples. But really, using the same theory and method, we could find force, we could find time, we could find mass, we could find change in velocity. Remember, whichever one that you're looking for, divide out the other one. So if I'm looking for velocity, I divide out mass on both sides. If I'm looking for mass, I divide out velocity on both sides. If I'm looking for time, I divide out force on both sides. If I'm looking for force, I divide out time on both sides. And then I will be good to go for any one of those answers. Okay, and that is the end. So